Okay, good evening everyone, and Assalamualaikum warahmatullahi wabarakatuh. Okay, and tonight we from first group will explain about the implementation of a complementary filter and Kalman filter. Okay, before that, let us introduce ourselves. And from let me introduce myself. And my name is Brian Panantun Karim. And here's my friend. Siapa?
My name is Feral Alasisku Samawibowo.
My name is Andrea Quintalatif.
My name is Julio Pradipa Nandika.
Okay, thank you for the introduction. Okay, before we going to about the main topic, if you want to build a drone or maybe a self-balancing robot, you your device needs to know which way is up. And to do this, we use an internal measurement units or MPU for short, and like the worldly popular, which is MPU6050. However, getting clean and usable angle out of the sensor isn't as simple as just reading a number. The MPU6050 contains two different sensors. They both have a fatal flaws. And the first one is the accelerometer. It measures the pull of gravity to find the absolute angle, but it is very incredibly sensitive to vibration and sudden movement. It is very noisy. And the second sensor is the gyroscope. It is measure how fast the sensor is spinning. It's perfectly smooth and responsive to quick movement, but over time, small math error piles up and the angle drifts completely away from the reality. And to get a perfect angle, we have to use sensor fusion, which is mathematical way to combine both sensor and taking the long-term accuracy of the accelerometer and mixing it with the short-term smoothness of the gyroscope. Okay, we will talk about the hardware setup, which will be explained by Ferrell.
Okay, the hardware setup. This project is straightforward because the MPU6050 communicates over the I2C protocol, which only need four wires connected to your own microcontroller, which is the VCC, the power. We can connect it to the 3.3 volt or 5 volt, depends on the specific breakout port. And second is ground. The third is SDA data that connects to the I2C SDA pin. And the last is SGL clock. It connects to the I2C SGL pin. The third is now filter. Now we actually run two different sensor fusion algorithms side by side to compare between both of them. The first is the complementary filter as the simpler approach. This filter is incredibly popular because it requires almost no processing power and it uses a fixed ratio to trust one sensor over the other. It uses 98 per 2 ratio. By using this 98 and 2 ratio, this formula will tell the microcontroller to trust the gyroscope of the 98% of the measurement because it is the smoothest, but mix with the 2% of the accelerometer absolute angle to constantly pull the measurement back and stop the drift. And the second is the Kalman filter, which is heavy duty on math. Unlike the fixed ratio on the complementary filter, the Kalman filter is a dynamic recursive algorithm and it will calculate the sensor angle and the gyroscope's creeping error. And it will simultaneously do that in a constant two-step cycle. The first is the predict cycle. The filter will guess the current angle based on the gyroscope speed. It also will increase its internal uncertainty value, mathematically admitting that because gyros drift, it will slightly less sure of its position. And the second cycle is the update. The filter will calculate the Kalman gain, SK, which is the thrust factor. It will the accelerometer will bounce around violently, then the K drops to zero and the filter will ignore it. If the filter prediction uncertainty has grown too high, K will rise to 1. And then we'll use this gain to snap the final angle toward the accelerometer measurement to re-anchor itself. And the, and the next is code explanation, which is will be explained by my friend Alan.
Yeah, so for the code explanation, in the setup, we write a 0 to the power management register to wake the MPU6050 up. Before entering the main loop, we take one initial reading from the accelerometer to calculate the starting angle. We feed this to the Kalman X set angle and the comp angle x. If we don't do this, the filter will start at 0 degrees and take a few seconds to slowly catch up to the sensor's actual physical tilt. Next, while in the gathering raw data and calculating delta time, in the loop, we request 14 consecutive bytes from the sensor to get the x, y, and z axis from both the accelerometer and the gyroscope. Crucially, we calculate the delta time using micros. Because the gyroscope measures speed degrees per second, we absolutely must know exactly how much time has passed since the last loop to calculate how far the sensor actually rotated. And finally, we feed our raw roll gyro rate and dt into the Kalman X and get angle and our one-line complementary filter math. We then print the results using a label value format so the Arduino serial plotter can graph them. Next, the demonstration results will be explained by my friend Julio.
Yes, so here in the demonstration, you can see the Arduino serial plotter, and then we physically move the sensor. For example, if we roll here, the raw accelerometer data is much noisier compared to the complementary filter and also the Kalman filter. And if we also see the pitch, there you can see that again the raw is more noisy compared to the two filters. So as you can see here, the movement, roll, and then pitch. And that's it for the demonstration.
Okay. Okay. I will explaining about the comparison and conclusion. Okay, both filters successfully solve the problem of raw sensor noise and drift, but they serve different purpose. For the complementary filter is brilliant in its simplicity. It costs almost zero processing power and memory. If you are building a simple two wheels and balancing robot or using a very basic slow microcontroller or maybe complementary filter, and the complement filter is usually more than enough to get the job done. And then for the common filter is mathematically optimal. It's require a dedicated library and heavier floating point math, but its ability to dynamically adapt its charge between the sensor based on the real-time noise and makes it vastly superior for high performance application. If you are building a drone, a rocket thrust vectoring system, or anything where precision is critical, the Kalman filter is the gold standard. I think that's all from our group. Thank you for listening. Wassalamualaikum warahmatullahi wabarakatuh.